All right, I think we are ready to go. So how's everyone holding up in isolation?
I mean, I have a dog, so that makes it a little easier.
Yeah,
Although it's
what kind of dog?
A Pomeranian.
You can, you could turn your video on and show us the dog.
Okay.
We're putting a video on.
Mm-hmm.
Nice dog.
Hey,
Look over here. Like, oh, there's a hand.
hey.
Yeah, I don't know if we've really made software verification quite simple enough that that your dog would gain something from this lecture, but he or she is definitely invited to participate.
You need to adjust the.
Yes, this is Tangerine, and he is a bastard. He's cute. He would like that.
Definitely cute.
Wiggle.
All right, I should note, by the way, that the dog immediately got more comments, more what do we call it? Student participation than the class usually does. So, I think it's just a good testament to sort of what's important in life right now. Software verification or dogs. Nonetheless, this is a class about software verification and not a class about dogs. So we're going to have to, despite that disappointing realization, we're going to have to truck along here. So what I'd like to talk about today is continuing on our theme of mixing proofs and computations. I'm going to talk about this idea called inductive types, which is going to sort of go further in this analogy that we started building last time between programs that compute certain values and proofs which prove certain propositions. So this is the propositions as types philosophy that I introduced last time. So if you remember, last time we kind of started with this idea of like what's a proof, and we kind of introduced this idea of proof rules. So for each logical connective like and, we had some introduction rules and some elimination rules. So introduction rules tell us how do I prove a certain kind of thing like A and B, and elimination rules would tell us how do I use a certain kind of thing, like a certain kind of assumption. So if I assume that A and B, how do I use that assumption? So we introduced these paired introduction and elimination rules, and noted that these were sort of basically, opposites. Like from one, you could get the other, because you kind of have this idea that if you introduce a proposition, then you should be able to get the stuff you introduced it with back out. And we built up from this idea of proof rules by adding little bits of syntax that represented proof terms. So we went through, and every time that we had a certain proposition, we also introduced a term for the proof of that proposition. And for each proof rule, we had a little bit of syntax that described that proof rule to record that we used a certain proof rule to prove that proposition. So here, for example, we introduced the lambda syntax for proofs of implications. And we also use this function application syntax for the elimination rule for implications. So that gave us this idea of proof terms, little bits of formal language to describe the proof rules that you've been using. And then given this idea of, once we had these proof terms, we started looking at them and we realized that those proof terms looked a lot like the terms in our ordinary programming languages. And that gave us this idea that I called propositions as types, which is that you could have one language that would include both proofs and also programs, proofs that prove certain propositions and programs that compute certain values. And the neat thing with having one language for these is that you could have syntax like lambdas that would be reused for both programs and for proofs, and data structures they could mix programs and proofs in between them. So that was what we talked about last time, introducing this idea of an analogy between proofs and the programs that we've been writing. Proofs that record proof rules in use, programs that record, well, basically the different kinds of ways that we build various values in our program. So what I'd like to do now is move on from move up really from what we discussed last time with these proof rules to really ask, where do the proof rules come from and how do I add new proof rules to record new kinds of data and new kinds of propositions. So that's what we'll be investigating in these next two lectures. And that'll really introduce all of the key ingredients that make dependent types, this language that allows you to mix programs and proofs in the same place. So I said I'm introducing this idea called inductive types. So what I'm going to do is I'm going to first talk about how can we define new data types for the program part of our proofs and programs to use, data types like natural numbers, lists, trees of values, that kind of thing. Then we're going to talk about the induction part of inductive data types, and specifically how it relates to recursion, as we do in ordinary programs. And the culmination of this investigation of the relationship between recursion and induction is going to be, I'll introduce this idea called proof by recursion, where we'll actually show that when we say proof by induction, what we really mean is recursively computing a proof. And I'll talk about that toward the end here. So let's begin by first taking this idea of an inductive data type. So far, when I've been introducing new logical connectives, and those have been things like and, or, implication, for all, there exists, we talked about not, and a few others, we've introduced them one at a time. So let's look at what it takes to introduce one of these data types. I like to introduce not things like pairs or functions that have sort of kind of obvious or like somewhat obvious proof analogs, but just like stuff ordinary programs deal with, like numbers and lists and trees, etc. Well, we recall way back in this class, we talked about like the axioms of piano arithmetic. And roughly speaking, those axioms were saying that like natural numbers are either 0 or n+1. Then they had some definitions of plus and times, and then they had this complicated thing called the induction axiom. And I want to look specifically at this first bullet point, which is that natural numbers are 0 or they're n+1. So just thinking about this colloquially, this is describing the kind of natural numbers that exist. I mean, specifically, formally, that axiom stated that all natural numbers are either 0 or n+1. So all natural numbers, all natural numbers are either equal to 0 or they're equal to n+1 for some kind of n. And that those two things are distinct. So 0 and n+1, they always produce different values. So we can think of this as saying that all natural numbers come via one of two mutually exclusive mechanisms, either via 0 or via something +1. So if this is telling us where natural numbers come from, we can see an analogy to other data types that we've looked at. So let's just look at, for example, let's compare natural numbers to OR terms, which we talked about last time. OR terms, we said, always come via either the left or the right constructor. So we see here that every OR term is either left of something or right of something. And of course, these are different. And remember that this idea that every OR term is either left of something or right of something, in some sense, that's related to the fact that we had two introduction rules for ORs. There are only two ways to introduce an OR term, namely via the proof rule that we ended up calling left, or the proof rule that we ended up calling right. So it looks like, by analogy, what we've done for natural numbers, where we have each natural number being either 0 or 1, that should also relate somehow to two introduction rules for natural numbers, one called 0 and one called something plus 1. And we can even look at this pattern for other kinds of data types that we've introduced. So for example, recall that we were talking also last time about AND terms, and we said that all of the AND terms are a pair A and B. And so here we have, again, because there's only one introduction rule for AND terms, now we see that we have for all C, but then we have only one thing in the OR. There's only one kind of place that AND terms could come from. And of course, in this case, this all of the different introduction rules produce distinct values doesn't really make sense anymore because there's only one introduction rule. So the basic idea that that this suggests is that any time that we have a data type and we can describe the possible ways of getting that data type, those possible ways are really introduction rules for that data type. Now, if that data type is an OR, you can think of that as a proof rule. How do you prove OR? But more broadly, if we have types like natural numbers that are not just propositions, they tell us, how can we produce a value of type nat? How do we produce a natural number? And the answer is that that natural number is either 0 or it is 1 bigger than some existing natural number. And other functions that return natural numbers like plus or multiplication have to be defined in terms of that. So what we're seeing here is kind of this idea that new data types, much like the way we introduce and OR and so on, can be introduced via new introduction by defining their introduction rules. And those introduction rules come from some more fundamental thing, which is the number of different values of that data, the ways that you can construct values of that data type. So, questions so far about this idea of introduction rules and their relationship to how a certain value is constructed? Go ahead, Skylar.
So basically what we're doing here, just to clarify, is we're using the introduction rules that we went over last time to establish like the existence of natural numbers within our proof network, right?
Yeah, in some sense, you could think of the type nat that we're defining here. If you wanted to think of it as data type, then it would be the type of natural numbers with values like 1 and 20 and 3000. Or you can think of it, if you really wanted to think of it as a proposition, you can almost think of it as the proposition that natural numbers exist. And there's like multiple ways of proving that. One is that you can prove that by pointing out that 0 is a proof that natural numbers exist. And another proof that natural numbers exist is if you had a proof that natural numbers exist, then that proof plus 1 would also be a proof that natural numbers exist. But I don't think it really makes that much sense to think of this. We're using the same mechanism of introduction rules, but we're using it not to introduce new kinds of proof, but new kinds of data types. Because remember, as we discussed last time, we have this almost identity, like equivalence between data types and propositions. And so now we're using the mechanisms that we had used for propositions, and we're finding that they make sense for data types as well. Does that answer your question?
Yeah, thanks.
Other questions? Okay, so I want to do a lot of sort of back and forth in this lecture between the slides and Lean to make sure that you are sort of connecting what is going on the slides to what's going on in the code. So I am going to exit out of the slides and switch over to this little Lean instance. And let's just take what I did here of defining 2 introduction rules for the natural numbers and see how that'd look in code. So when we define a new data type via its constructors, in Lean, we use the syntax inductive. So I'm going to say that we're inductively defining something called nat. And I am going to do this weird command. Oh, sorry. Which will just keep Lean from realizing that there's already something called nat out there in the world. So I want to define natural numbers nat, and I want to do it by introducing 2 different introduction rules. So one is going to be 0, and I'm going to call that introduction rule 0. So 0 is a natural number on its own. And you can think of what I've written here as what goes on below the line over here, 0 colon natural number. And there's that line above that. And then in this case, I have stuff both below the line, n+1, and stuff above the line. So the way that you write that in Lean is you say +1, and then you write nat to nat. And so one way to think about this, what I've written here, is as something analogous to some proof of nat this. And Lean implicitly fills in a name for that proof of nat and applies it into +1. So here with this syntax, I've defined a new data type called nat. I've given it 2 constructors, 0 and +1. And now I can use those constructors to define terms of this type. So for example, I can check what is the type of nat.0. And it says nat.0 is a natural number. And if I instead give it nat.+1 of nat.0, I can see that this is also a natural number, which we might colloquially refer to as 1. But you know, this is the way Lean thinks of it. You can see that that is a natural number that we've defined as well. And note that you know, even though we've called this nat, Lean has no real idea that this represents the natural numbers. So if we write reduce to ask Lean to give us the, you know, real fundamental primitive description of what this term actually looks like, you find that it is in fact just exactly what we wrote, because the most fundamental representation of this value is the set of introduction rules we used to introduce that term. So we introduced nat here via nat.0 and here via nat+1, applying it to its hypothesis nat.0. And this is kind of analogous to what we could have done to define OR, where we would have given it arguments. But fundamentally written the same idea, where we say that we're defining a data type called OR. There are going to be 2 constructors for it, left and right. And left is going to require a hypothesis of type A, and right is going to require a hypothesis of type B. And again, we can check what you know, left 2 is, or dot left 2. And In this case, unfortunately, I need to explain. Oh, goodness. Oh, man. There we go. Sorry about that. This underscore here is I'm simply asking Lean to ignore this B term. So I guess here I could do like some other type like nat. And now I said that I am creating a term by applying my constructor or my introduction rule called left. That introduction rule requires a hypothesis A of type A. So I've picked A to be int in this case, and I've given it a term of that type, namely 2. And Lean also wants to know what is B in this case. So I've told it that should be nat. And so it is saying that this is a term of type OR int nat. So you can see here that the same mechanism that we've applied to introduce natural numbers, which is sort of a data typey thing, we can apply that same mechanism here to introduce a more proposition-y thing, namely ORs. So questions about this sort of unity that you've seen between natural numbers, between defining natural numbers and defining more proposition-y things like OR. Or just questions about Lean that you've been itching to ask because it doesn't make that much sense to you. Go ahead, Pranav.
I'm a bit confused how these things are binding in Lean. Like, for example, you said here in line 19 that 2:int is being binded to A, and then nat is being binded to B. Like, shouldn't it be the other way because A is the first?
Yeah, Lean's a little weird in how exactly it handles this. You might think, okay, let me actually fill this out completely. It looks more like this. So what I put this @ sign here, this @ sign here means something along the lines of Lean, no funny business. So OR is going to take 2 arguments, which are both types. So any of the OR constructors need to know what the 2 types A and B are. So here I've told it that A and B are going to be int and nat. And then for left, I need to additionally introduce a term of type A. You might think of that as a proof of A, but since A here is int, it's not really a proof. It's more like a term of that type. So I need to introduce a term of type int. So here I've written down 2. So I could just write 2 here. And now it knows that it is an OR of A and B being int and nat. And to call this introduction rule, I need to give it a term of type A, so a term of type int. So 2 is a term of type int. The thing I did before without the @ sign was just a slightly different syntactic quirk that Lean has. So sorry about that. I'll try to use the @ sign from now on because it'll be a little clearer.
Yeah, thanks.
Yeah, so that was a good clarification. Anyone have any other questions? Okay, great. Well, let me then go back here and ask the next question, which is, so far we've discussed defining a data type in terms of its introduction rules. But if you recall, when we talked about different logical connectives like AND and OR last time, we said that they not only have introduction rules, they also have elimination rules. Introduction rules tell you how to prove a certain thing. Elimination rules tell you how to use a certain assumption. So what are the elimination rules going to be like for NAT? That's a little weird because given that it's not totally clear how you think about natural numbers as a proposition, it certainly is not clear how you would make use of the assumption that natural numbers exist or something like that. So let's try to work by analogy to resolve this question. I'm going to use an analogy from OR because, as you've seen, OR is kind of similar to NAT. It also has two constructors, and it's something where we understand the elimination rule. So OR has two constructors. We saw that last time, one called left and one called right, and you just saw me implement these two in Lean. So just to remind you how these go, since it's an introduction rule, we have the logical connective we want to introduce below. There are two ways to prove A or B, either prove A or prove B. And then because it's now that we're writing out the proof terms, we have names left and right for these two introduction rules. And we also have names for those two assumptions that we reuse in the introduction rule. So here we've written down the two introduction rules for OR, and those are the two constructors, I call them, the two ways of creating a term of type OR. And its elimination rule, the elimination rule for OR, has individual assumptions for each of those constructors. So in the elimination rule, we have the thing that we want to make use of, the assumption we want to make use of. So that's a term of type A or B. And then for each constructor, like left and right, we have a assumption we need to fill in the elimination rule, an extra thing that we need to be able to produce in the elimination rule. So these additional things, f sub a and f sub b, I've written, are, you see, arguments, are functions. Their output is the actual thing that we're trying to prove, but their assumptions are the two inputs to those two constructors. So you can see that we have that left, for left, we need an assumption of type A, and f of A, which is that thing in the elimination rule corresponding to left, takes an input of type A as well. And similarly, right is a constructor, and f sub b, which relates to it, takes b as an argument, just like right does. So what we've got here, we've got sort of a hint at a schema for how to write down these elimination rules. In the middle, we're putting the term that we're eliminating, and that's always going to be some p of the type that we are writing an elimination rule for. And then for each of the introduction rules that we wrote down, that gives us an additional thing that goes above the line. And that thing is going to be a function. That function's output type will be the thing we're trying to prove, and its inputs will be the various inputs to the constructors they represent. So I know there's a lot of sort of squiggling on this slide, so let me pause here for questions about this sort of analogy that I've set up, or this connection I've set up between the introduction and the elimination rules. And by the way, a side note, right? Why should there be a connection between the introduction and elimination rules? Well, as you recall from last time, there's some kind of rule that like the elimination rules and the introduction rules are like kind of opposites of one another, because you don't like get like free information or something like that. So that's what we're leveraging here. So we have the constructors, and then the elimination rule has to kind of be the opposite of that. So let's see how we can take this take this OR stuff. Note that in OR we have two constructors, while NAT also has two constructors. So let's just try to transfer what we have about OR into something about NAT. So let's first look at our two constructors. We have one constructor called 0 and one constructor called n+1. And so if we just sort of follow along the schema from last time, that tells us what is our elimination rule going to look like? Well, it's going to have n:(nat) in the middle here. Then there's going to be some kind of output type, which I've called C. And then because we have two constructors, we're going to have two additional function arguments, which I've called f sub 0 and f sub +1 for the 0 and the n+1 constructors. And these functions, their output type, Okay, sorry. Yep. So these functions, they have an output type, C. That should be C. And their input types, so they all have the same output type. And their input types are the inputs to each of the constructors. So here, nat is there's a nat input to the n+1 constructor. So f sub +1 has a nat argument. And there's no input at all to the 0 constructor. And so there are no arguments to the f sub 0 function. So what we've done here, we've just kind of blindly taken the stuff we wrote down for OR. We've just created by analogy something like that for NAT. And you can see that I've just like for OR, I've invented some kind of new syntax to describe this elimination rule. So what we've done here, this elimination rule, right? That's just something we wrote down by analogy to OR. There's not immediately any reason to think that it's the right thing, but it follows the same pattern. And it turns out that this elimination rule we've written down also starts looking a little bit like another one of those piano axioms we talked about in the beginning of class, namely the induction rule. So in the induction rule, it looks a little bit different, but it's a little bit similar too. So here in the induction rule, we also have some kind of general NAT, and we have some kind of general output, except that output, instead of being C, is P of N. Instead of being just a type, it is a property of a natural number. But recall that in our world, the analogy between types and propositions, so if we have a proposition about a natural number, that is kind of like a type. And then instead of this f sub 0 and f sub +1, which have types involving things like C and NAT, we instead have propositions, which again, remember, are types in this type propositions as types world. So instead of C, we have P of 0 here. Instead of C, we have P of n+1 here. And then instead of this NAT, we have P of N here. So you can see that the elimination rule we wrote down is actually in this analogy between types and propositions, in this equivalence between types and propositions we're exploring. The elimination rule we've written down is actually the same thing as the induction rule. The induction rule that we discussed in the beginning of class kind of disconnected to this idea of introduction and elimination rules. So, questions about this sort of weird correspondence we've discovered between the elimination rules that we'd sort of naturally write down and the induction rule that natural numbers come with. Okay, so let me try to demonstrate the same thing now in code. We over here ended up defining the natural numbers via 2 introduction rules. And when we do this, under the hood, Lean not only defines nat.0 and nat.+1, corresponding to those 2 introduction rules, it also automatically defines something called nat.rec. And nat.rec, rec standing for recursion, is the elimination rule that we were talking about just a moment ago. So let me just put an @ sign in front of it, which will make that a little less weird looking. And let me actually grab this, which is Lean's type for nat.rec, and just write it down here with some new lines. So I'm going to just take what Lean has written down here and do a little bit of renaming to make it a little more normal looking. So this big, weird, like 3-sided box type thing, this is an alternative syntax in Lean for all. So let me just replace that everywhere. And now you can see that the first thing that Lean for all's over is this thing called C, which is a function from NAT to sort U1. So sort U1, not clear what that is, but let's write prop for proposition, or maybe since we understand that propositions are actually types, we'll write type here. And in my slides, I haven't been calling it C, I've been calling it P. So I'll just rename C to P. Now we can see that nat.rec, which applies to an arbitrary P, it's got a function, it's got 2 arguments, and then it produces an output. So these 2 arguments, well, this one is P of 0. And then this one is for all A, I'm going to replace A with N because we're talking about natural numbers here. This one says for all N, if P of N, then P of N plus 1. And if that's true, then for all natural numbers N, we have a P of N. So let's just compare that to what we saw over here. We have P of 0, we have P of N implies P of N plus 1, and then we have for all N, P of N. So you can see that what Lean derived here as the type of nat.rec, that nat.rec, that ends up being the same as this induction principle that we wrote down, this induction rule that we wrote down, and that is in fact the same as the elimination rule that we wrote down by analogy as well. So you can see that this induction rule that we've been discussing, that in fact is the elimination rule that corresponds to the definition of NAT with 2 constructors that we've written down here. And okay, so let me take questions about that, this analogy between induction and elimination rules and what Lean did automatically here.
Are you going to show an example of how to use nat.rec?
I will. So we will talk about using this induction rule shortly.
Awesome, thanks.
Very reasonable question. Any other questions? Okay, so just to summarize, we've talked about how you introduce new data types in this propositions as types world. And we said that to introduce new data types, you need to write down the introduction rules for that data type. And then once you've written down these introduction rules, there's a corresponding elimination rule. So when that introduction rule is something, when the introduction rules are the introduction rules for OR, the elimination rule that you get is this case analysis elimination rule. And when the introduction rules are the introduction rules for natural numbers, 0 and n plus 1, then the elimination rule you get is proof by induction, is the induction axiom. And we've seen that in Slideware, and then we saw the same thing here. So the corresponding version of that in Lean code, we can define a new data type using the inductive keyword. And to do so, we have to list the constructors or name the introduction rules for that data type. And when we do that, Lean will, define those introduction rules, but it'll also automatically define the elimination rule, which it always calls name of type dot rec. So what Lean is doing is it's looking at all of your constructors, in this case, these 2 constructors. It is doing that same analogy thing that we did on Slideware to come up with the elimination rule as well. So we can see the same thing go on if we look at, for example, or.rec. And again, I'm going to put an @ sign. And again, to make this a little more readable, I'm gonna copy and paste it. So or.rec says, well, first of all, it's or A and B. So it makes sense. We're going to take A and B arguments. And it's got some property P. And you can see that in this case, it's a little bit weird. This property P isn't just some type that we're proving. It's a type that can be dependent on which of A or B is true. But we can always say that let's just say that that function ignores its first argument. In that case, P, which I should finish replacing with C here, is going to, we don't need to pass it that first argument as well. So I've now replaced C of something just by P everywhere. And now you can see that there are two arguments to this elimination rule. So what are those arguments? Well, this one says, remember these capital Greek pi things are actually just for all. So here it says for all proofs of A, P is true, which is really just a way of saying A to P. Here we're saying the same for all proofs of B, P is true, so that's just B to P. And then this is saying, again, we're not making use of this term N, so we can just say or of AB implies P. And so now this or.rec that we've massaged a little bit, that looks exactly like this analysis by cases, where if you have or of A and B, and if A implies P and B implies P, then you can prove P as well. So you can see that again, the elimination rule that we've written down works both for natural numbers, where it produces the induction rule, and for or, where it produces this case analysis rule. So questions? Okay, in that case, let's look at a few more inductive data types. So I have two ideas of two more inductive data types that I want to introduce. One is going to be the Booleans. So if we talk about the Booleans, we think, what are the different ways that you can create a Boolean? Well, there are in fact just two Booleans, one called true and one called false. So here I've defined a data type bool and given it two constructors, two introduction rules, true and false. And so naturally, it has now created bool.true. Lean has now created bool.true and bool.false, which are both terms of type bool. And Lean has also introduced bool.rec. And I'm going to do the same kind of massaging I've been doing for all of these others. I'm going to copy this type here and say, okay, bool.rec. We got this pi. I'm going to replace that with a for all. C, we're going to replace that by P everywhere. And then we have now bool to sort U1. I'm just going to call that type. And I'm going to put all of these arguments on the same row. And so what this induction principle says, or this elimination rule says, is to prove something about all Booleans, you need to prove it about true and prove it about false. And then you will know it about all Booleans, N. And that makes sense because there are only two Booleans, true and false. So if you prove something about true and about false, you should now know it about all Booleans. And in some sense, this is the axiom that tells you that there are only two Booleans. It tells you that to prove things about all Booleans, it's sufficient to prove about these particular two. So that's what a definition for a bool looks like. We have these two constructors, and then the elimination rule in this case basically tells us that all Booleans are either true or false. And if you think about it, that's what the elimination rules have been telling us for NAT and OR as well. The elimination rule for NAT tells us that there are only two kinds of natural numbers. So to prove something about a natural number, you have to prove it about those two kinds. You have to prove it about 0, and you have to prove it about n plus 1. And similarly, our rule for OR tells us that there are only two kinds of OR terms. So to prove something about all kinds of OR terms, you must just prove it about OR.left and about OR.right. And so that's another way of thinking about what does the elimination rule do. It basically lists all the possible ways you could have constructed that term and tells you that those are the only ones. And that makes sense because we have that term as an assumption. You can ask, how could it have been constructed, and make use of those. So questions about the Boolean definition? In that case, I'm going to do one more. And actually, let's turn this into a little bit of an exercise. What I'd like to do is I'd like to define lists. And I'd like to define lists kind of similar to the way they are linked lists. So they're gonna be a cell that points to another linked list. So think about, let's take 30 seconds to think about what are the ways that you can construct a list. And then once you've written that down, try to figure out what would an elimination rule for lists look like. So I'll put 30 seconds on the clock. So you should try to figure out what are the introduction rules, and then we'll do the breakouts and try to figure out what are the good, so you can discuss what a good elimination rule would look like. Okay, so hopefully you've had a chance to think about what are introduction rules for lists going to be like for linked lists. So I'm going to put you into breakout rooms and have you discuss what the introduction rules you're thinking of would be like. And then also you can chat about what an elimination rule would be for lists if you can achieve consensus on what the introduction rules are like. You guys done? You're back? All right, I see a lot of people joining, so I'm gonna close the rooms. Okay, so you've had a little bit of time to discuss introduction and maybe even elimination rules for lists. So let me first ask someone to tell me what are the introduction rules that you've come to consensus on for lists? Anyone? You can do the raise hands thing. Go ahead, Skylar.
So I'm still fuzzy on what the lean syntax for this would be.
That's fine. Yeah, you
But-
can just say it out loud.
The idea that we came up with was to have basically 3 different rules.
Okay.
The first one would have nothing on above the bar, and then below the bar it would be, or I guess it would basically be something along the lines of, if this is a head node, it's a part of the list. And then the other one would be, if this is a tail node, it's a part of the list. And then the final one would be, given some node in the list, node arrow next is in the list.
Okay. So let me try to sort of combine those together. So you're saying, okay, so the way you're thinking about it is you're saying you've got your linked list, which is a bunch of these little pairs, right? And then at some point there's a tail node with no forward pointer, no next pointer, right?
Yeah.
And you're saying, you're trying to answer the question of like, what is in the list? And you're saying, well, this is in the list. So you kind of want to say like, you know, this is a list, something like that.
Yeah.
And then you want to say, this is also a list. But like if that is a list, something like that.
Yeah.
Okay. And then you're sort of also talking about like what is in the list. So you're saying like here alpha is in the list and here alpha is in the list, or also anything in P is in the list. But right now it's not really in the list that we're talking about, but just like what are lists? So you said you've basically given 2 introduction rules for that. You said here are 2 introduction rules, one for the tail node and one for the not tail node. What was the third one? I think I missed that.
The third one was for the head node, but now that I think about it, I think it's redundant.
Ah, I see. You wanted to sort of have like a separate, like special node that is like a head node.
Yeah.
Right. But that doesn't look that much different from one of the interior nodes.
No.
Yeah, you could separate those out if you want, but you also don't have to. Okay, so just to turn this into a definition of lists, let's just say there's got to be something inside this box. So let me say that that's some type A. And I'll just give it a type. I'll say it's from some big type A. Does that make sense? So we can now turn this into a bit of lean syntax. We could say a list of big A's here. That's going to be either a tail node, and for that tail node we need an A, and we get a list. So we need an A, we get a list, big A. Or it is an intermediate node. And for that, we need an A and a list, and we get a list. So this is a perfectly good definition of lists. We've got 2 types of constructors for tail nodes and for intermediate nodes. Skylar?
Is there any risk caused by calling one of your types int?
No, because lean actually refers to these as list.int.
Oh, okay.
Yeah. That's it's actually the same reason that I can go ahead and call this nat, even though lean does have natural numbers built in, because way up in the beginning here, I told lean that it's actually called foo.nat, and so lean doesn't get confused. Yeah. I mean, you could call it, you know, body or neck. I don't know what your sort of anatomical analogy here for lists is. Did anyone have a different set of introduction rules for lists? Go ahead, Kelvin.
You could just have like the empty cons construction.
Can you expand on what you mean by that?
So like empty is a list, and then cons a list is a list.
Okay, so you're saying you're gonna have two constructors, empty and cons, and empty is just a list on its own. And then cons takes an A and a list and produces a list. Is that what you mean?
Yeah.
Okay, right. So these are slightly different types in that here you can have empty lists and here you cannot have empty lists. A list has at least one thing in it. I guess it's kind of like almost like a weird like dictionary definition kind of discussion here of whether a list of no things is a list, but it is the case that generally speaking in programming, we think of a list as possibly being empty. So I'm gonna stick with this definition of list here, but it's, you know, it's perfectly legitimate to do them either way. And by the way, I should note that the reason that cons is called cons, you may have wondered, like, why is that the term for adding a thing to a list? Con stands for constructor. But of course, empty is also a constructor. They are both ways to introduce a list. A list is either empty, so no empty introduces an empty list, and cons introduces a list containing elements. Okay, so those are two different variants of how you could define lists. And now I want to know whether any group had some idea of what an elimination rule for lists would look like. And again, an elimination rule is a way to make use of a list to produce an element of some other type. And that type, you can think of it as a proposition about that list. That's a nice way of thinking about that type, because remember, propositions are types. So an elimination rule should look like something like, should have a type something like, you know, list to, and in particular for all lists L, P of L, except there's going to be some other arguments here. So did any group come up with an elimination rule or get any progress on what that might look like?
I had a guess,
Go ahead.
and this is
Guesses are
Shelter.
great. Yeah.
Is it? I'm kind of thinking it as like an array, sort of. But if we're eliminating the list, are we just accessing or getting the type that the list is wrapping around, in some sense?
Or there's
like
definitely going to be
thing?
something about the type of the elements, right? Like, I mean, if you prove a property about a list, you're presumably looking at the stuff inside the list. So you have to, you're right, we definitely need some kind of access to those elements. And in fact, this elimination rule is going to start with a for all A, so that we can talk for all L in list A. Other questions? Sorry, other guesses or ideas of what this elimination rule would have to look like? Go ahead, Kelvin.
So I assume you'd want something like a fold L or something. Like you want something that accumulates over the list into another type.
Okay, right. So you're saying we want to sort of go down the list and produce some kind of other type. So that's this P of L. That's the kind of type that we're accumulating over. So in fact, I'm going to write down that we've got some kind of P, which is from list A to type. Any other ideas of what an elimination rule might have to involve? So Calvin, you mentioned that we need this P and we need to somehow accumulate into it. So do you have some sense of what that accumulating into it is going to look like?
So you want a P of L, and you also want a function from A to P of L. No, sorry, a function from P of L and A to P of L.
Okay, so you're saying we're going to need something from A to P of L to P of L.
And then a P of L.
And then another P of L. Okay, so I think what you're trying to say here is like, look, if you have a list, right? We have a list here, L. Then there are two ways you could have made that list because there are two introduction rules, two constructors for list. So one of them is going to be empty and one of them is going to be cons. So you're going to have to, if you want to deal with an arbitrary list, it's enough to deal with empty lists and with lists that are built with cons. So in particular here, we want a property not of L, but we want to say there's one of the two cases is that L is the empty list. So we want a property of the empty list. And in the other case, we want a property of a cons. Sorry, property of a cons. And to do that, we're going to need some kind of A and some kind of L. And I'm going to call this L prime just so that we don't confuse them. So what we're saying here is if we want to prove something about an arbitrary list, we want to prove P of L for an arbitrary L, then it's enough to prove it about the two forms that list could be in. It could either be an empty list or it could be a cons onto some other list. So those are the two cases we need to deal with. Hence, we're going to have a P of empty for the case that it's an empty list and a P of cons for the case that it's a cons list. And since we're talking about a cons A L prime, we need to introduce those two variables. And if we are looking at that property of cons onto some list, then we can assume inductively that it's true about that list as well. So that's that accumulation step you were talking about. So this right here is in fact the elimination rule for lists. And we can actually check that by saying, well, the syntax is a little wacky here. Let me restore that. So we can ask Lean, what is the elimination rule for lists? And as usual, I'm going to do a little bit of massaging to make it look like what I wrote down here. So it says list.rec. Let's do those changes that I always do. So we're going to move that onto its own line over here as well. Now we're going to take these pies and turn them into for alls, and you'll see that it's starting to look more and more like what we wrote down here. So you're saying, see that over here we have a for all A at the very top. Then we have a for all C from list A to type. So I'm going to rename that with P just to make it the same as everywhere as below. And then you can see that here we've got P applied to list.empty A. So that's just P of empty like we wrote down over here. And over here, this is something that ends in P of cons. So let me just do a little bit of renaming here. I'm gonna, instead of A1, I'm gonna use L. So here we've got P of cons AL, just like we wrote down over here, P of cons AL. And it says P of L to P of cons AL, just like we did here. And it has this for all over A and L. And at the end here, it has this for all L in list A, P of L. So you can see that Lean has actually written down the same exact elimination rule that we've constructed here. And the reasoning again is that for this elimination rule always looks kind of similar. It says for all P from the type we define to type. So this is our type that we're trying to extract out of a list. In other words, we think of this as maybe a property of that list because propositions are types. It is always going to say for all lists P of L, and it's going to have arguments, and those arguments are going to be related to those two constructors. This one for the empty constructor and this one for the cons constructor. So any additional questions about elimination rules? Okay, in that case, let's move on to talking a little bit about using these elimination rules. And in particular, let's look at recursion. So I want to dial a little bit back to just some experience you've had, programming recursive functions. So let's look at, so far what we've done, we've defined new data types. We've defined them by their constructors. Those constructors have arguments. Each of those constructors, that's an introduction rule. And then we have these elimination rules. So that elimination rule is based on those constructors. Basically, it has for each constructor, it has a function that takes those constructor arguments, returns C. And the induction rule is basically that, but we think of that C as a property P of that constructor. So now let's look at just, let's start thinking about how we can use these induction rules. So let's start with some simple recursive computation, like the length of a list. So what I've done here is I've said length, that's a function. It takes a list and returns a natural number. For an empty list, which I've called nil here, the length of the list is 0. And for a cons, it's the length of the tail of the list plus 1. And this is your sort of standard computation of the length of a linked list. You just walk down the list one by one, recursively adding up the number. So what we've got here is we've got a function from lists to some other type. So this is somehow taking in an argument or an assumption of list type and producing something else. So we know that to make use of a list, like here, to make use of a list passed in as an argument, we use the elimination rule. So let's put up that elimination rule that we just wrote down. It says, just to rehash, if you have a list and you want to compute something out of the list, you need to, if you want to prove a property of that list, you need to prove that property of the empty list. You need to prove that property of cons, assuming, of course, that property is true of the rest of the list. Yep, Calvin, question?
Yes, a little bit of a question real quick. So I'm not entirely sure if anybody else wonders this, but so cons here has 2 arguments. And so our function here is taking both arguments, I suppose? Or
are you asking sort of about this like pipe syntax that I'm using here?
Well, so
like how exactly that works?
Elimination rule in general, if it just takes the A in the list, or if it takes the A and the L.
So it takes the A and the L, it actually, and I see I have a bit of a typo here. There should be a prime there. The L, it takes not just the L itself, but that property being true of that list. So you want to think of this as somehow, like if this wasn't P, if this was like C, right? You kind of want to think about this as C to C.
Sure. Okay, sorry. Ask later, maybe, if I get a better question.
Sure. Yeah, no problem. We can definitely return to it. I guess what I'm trying to say is, in this elimination rule, for each constructor, you're going to have a term. That term is going to produce an output that is the type that you're trying to return, here P of something. And it's going to have arguments related to the arguments of that constructor. So here our constructor has 2 arguments, A and R, which is a list. So for A, we have this for all X. And for that list, we have P of that list. And that's the way the elimination rule is built. So I want to try to match up this recursive definition we've written with this induction rule, because we know they need to be related somehow. Clearly, this 0, that tells us how to compute the length of an empty list. So that's kind of like P of empty, right? It's the length of that empty list. And here, when we've written cons, well, that tells us that that's the other type of way that you could build a list. So that's got to be the other argument to the elimination rule. So here we've got a cons A and R, and that's got to be this for all X and for all L prime. And then the output here, length of R plus 1, that's the length of the cons, but it's in terms of length of R, which is here length of R. So you can see that this definition that we've written down using this pipe syntax, where we've got like one thing for every constructor, that actually has bits and pieces of this elimination rule. And in fact, we can rewrite it to have the form of a call to that elimination rule. Here's what that's going to look like. Little animation bug, sorry. It's going to say, it's going to be, we want to define the length of a list. So it's a function of a list, and it's going to recurse on that list. And it's going to return P of L is always going to just be a natural number. And it's going to have two cases. One case will be, what do you do for an empty list? And the other case is going to be, what natural number do you return for an empty list? And the other is going to be, what natural number do you return for a cons? So for an empty list, we want to say, well, there actually aren't any arguments. We just need to return P of empty list. P of something is nat. We need to return a natural number. The natural number that is the length of a list, that's 0. And if we're talking about the inductive case, we say, well, we have for all X. So here we have lambda X, because remember, lambda is how you introduce something of for all type. Then we have for all L prime. So I've got my L prime here. Then I've got P of that L prime. So that's got to be the length of L prime. So I'm calling it here length L. That's another argument, because this is an implication. And again, lambda also introduces implications. And then I just need to compute the length of that cons, which is the length of the tail, length L, plus 1. So what we've done here is we've rewritten this in this pattern matchy definition, where we had a different expression for each of these constructors. We've rewritten that directly into a call to the induction principle on lists. And this sort of rewriting, that's something that Lean does internally automatically. I can demonstrate that by just going here and actually implementing that definition. So we already have lists defined over here. So now I can say definition length. It's going to be for all A, list A to net. And I'm going to define it first for empty. It's going to be 0. And it actually, we're using our definition of, are we using our definition of net? I think we are. So that's nat.0. And oh, sorry, A, empty. There we go. And in the other case, we have list.cons of A, L prime. And in this case, we want to return length L prime plus 1. And actually, for our natural numbers, plus 1 is defined as is called nat.plus1. trying to figure out what it's unhappy about here. You know, I think I'm getting confused just about the difference between our list and not our list, but here I've dropped down into the Lean's built-in definition of nat and list, which is really identical to what we've written up here. So I've defined length in the sort of the usual way that you might expect. And then if we ask Lean to print length, oh boy, print something terrible. Wow, that's really something. You know, that's crazy. Well, because that's crazy, let's try to define length again, just using the list recursion principle or induction principle. So I want to define it again, but this time, instead of using this pipe syntax, I'm just going to write down the definition. And that definition is going to use list.rec. So it's helpful just to see it again. It says we have some type that it's a list of t, and then we write down a property, and then we write down those two cases. So I'm just going to do exactly what I did over here. I'm going to take list.rec. I'm going to say this is a function. It takes a and a list L. It's going to call list.rec on a. Then if we look at list.rec, the next thing it wants is what type do we return? Well, that is a function from lists, and we always want to return a natural number. And then the next argument that we need to provide it is what natural number do we want in the empty list case, and what natural number do we want in the cons case. So in the empty list case, I want the natural number 0. And in the cons case, I'm going to have, just like on the slides, it's going to be head colon tail, head constant to tail, or as I called them, x and L prime. And then I'm going to get the length of L prime as well, and I want to return length L prime plus 1. So this, here we've defined the term we deduct over, and we just want to apply all of this to L. And you can see that once I've defined it, Lean is happy with the definition. So in fact, we can ask it to compute, for example, we can ask both this one to compute the length of this list of integers, and it says that the length of that list of integers is 3. And then we can ask it to do the same with our alternative definition. And it'll again compute 3. So these are really the same length function. It's just that this one is written in this pattern matching syntax, and this one is written in this direct call to the inductor. So basically what we've seen here is that we can use induction both to prove properties about all elements of some data type. Like, so for numbers, you prove a base case P of 0 and prove an inductive case that P of n implies P of n plus 1. But it can also be used to compute recursive functions. You have to implement a base case, namely f of 0. You need to implement the recursive case, f of n plus 1. And you do that in terms of f of n, which you might even write something like this. So to really emphasize the similarity between these two cases. So all we're doing here, we're saying that proving properties and writing programs both end up using this induction rule. And that makes sense because inner language proofs are programs. And in fact, we can think of proving properties of all natural numbers as really writing a function that constructs such a proof. And just to emphasize that similarity, I want to talk a little bit about this specific idea of using induction to prove properties and what that means internally. But before I do that, let me take any remaining questions. Actually, I think we are low on time. The demos took a little longer than I thought. So let me quickly go through that material, and you can look at the slides online for the course updates. That's just going to be details on the final project, and that'll be on Canvas as well after the lecture. So what we've done so far, we've introduced this idea of inductive data types. We've used them to define things like natural numbers and lists via their introduction rules, their constructors. Then we discover that the induction principles that we talked about earlier in the class, that actually ends up being the elimination rule for natural numbers, and that those are somehow related to recursive functions. Let me just re-emphasize that relationship by coming at it in the other direction. So suppose we want to prove this theorem, that 0 is less than or equal to all natural numbers n. That's a true theorem because when we say natural numbers, we mean 0 and above. Well, if we want to prove this theorem by induction, that's going to mean proving the base case and the inductive case. That base case is going to be that 0 is less than or equal to 0. The inductive case is going to be that n plus 0 is less than or equal to n plus 1, assuming 0 is less than or equal to n. And we can write down this proof in lean. We could say that, well, this theorem, that's going to be for all n, 0 is less than or equal to n. To prove it by induction, we call the induction principle rec, or rec on just does the same thing in a different, is rec with just the arguments in a different order. So this is just calling nat.rec. And then it turns out that lean actually comes with proofs that 0 is less than or equal to 0, and that 0 is less than or equal to n, 0 is less than or equal to n plus 1. So we can just write down these terms directly, and what we get as a result is this proof by induction in code that looks like that. And if we had time, I could copy and paste it to lean to show you that it type checks, but it does. But this looks quite a bit like that recursive length computation that we discussed a few slides ago. So in that length computation, what we did is take the pattern matching style definition with the pipes and one expression per constructor, turn it into a call to nat.rec or list.rec. Now let's do the reverse. Here we've got an expression to use in the nil case and an expression to use in the n plus 1 case. So if we just uncompile it, we should take this expression, copy it into the 0 case, this expression, copy it into the n plus 1 case, pf here, that's going to become our recursive call. So what we've done here is we've taken this proof by induction, which we think of as a proof of a theorem, as opposed to a function that computes something, and shown that that can actually be rewritten directly into this recursive style. You might call this proof by recursion. And again, it makes sense because proof by induction, really the same thing as recursively computing a proof term. So when we say that to prove by induction, you have to prove a base case p of 0, that means you've got to implement f of 0, which is going to have type p of 0. Implement, write down a proof of the thing you want applied to 0. And similarly, for this inductive case, we need to implement f of n plus 1 in terms of f of n. And so in our propositions as types, proofs as programs world, induction and recursion also end up being the same kind of concept. So this unification that we've seen between simple data types like pairs and functions, and then logical properties like implication and conjunction, that also sets up an analogy between recursion, the sort of thing we do ordinarily in our programs, and induction, which is this mathematical technique for constructing proofs. Because if your proofs are programs, then proofs by induction are really just recursive computations that produce proofs. So that's what I've got for you for today. Since you're at your computers, now is a great time to fill out the course feedback. In the next class, we'll sort of conclude our dive into dependent types by talking about the dependent type part of dependent types. Meanwhile, you're all working on your class projects, I am sure. So you might want to check the slides for some quick details on the final project presentations. which are going to be due in a week. So you should just check the slides for details on that. And what we will do next time is we will discuss this idea of inductively defined predicates. Because if propositions are types and we can inductively define types, we should be able to inductively define propositions. And we'll talk about what it means to induct over a proof and how that introduces multiple terms, multiple variables that need to be coordinated. So that is for next time. Until then, you have your class projects, your class project presentations, and the course feedback to fill out. So I will see you all next time on Tuesday to discuss type dependency. And I'm happy to take any other questions you have. I just wanted to make sure I stay within the allotted time.
Do you mind if I ask a question?
Yeah, go ahead. Questions welcome.
So I think I understand what I was reading, what I was saying better. I was reading about these things called paramorphisms,
Bro.
which I think are like that they're like folds on lists, but they also take the rest of the list. Like the function
Okay.
would operate on the elements, but operates on the list and the rest of it. And I was wondering why you can define this like generic reduction on lists by just a fold, and you don't ever need like the rest of the list, or like in general like trees, if you don't need the rest of the tree. Or
Yeah, so let me do a simple case of that, which is for natural numbers. So what you're saying is, well, actually, no, hold on. I think I realize I don't understand your question. So what you're talking about is so you're saying like, okay, there's normal fold, which is like takes list of A, and it takes some B and some function A to B to B, and it produces a B. Is that right?
yeah,
Which we think of as like for any list, then you've got initial value, then you've got update value, and then you've got output.
yes.
Cool. And you're saying, well, what about this alternative fold, fold prime, where this not only gets A, the term at the head of the value at the head of the list, but also the rest of the list.
Yeah, like it takes the entirety of like the list element, like the
Yep.
cons.
Yep. Okay. Well, if you compare that to the list, let's just copy this use of the list recursor. You'll see that here we've got our A. We have our B. So these are our definitions of A and B. We've got our list of A right here. That's called L. We've got our initial value 0. But the thing that's of interest is this update step. So this update step takes an A, a list of A, and this, which you can think of as, well, it's a natural number, which is our B, and it produces a natural number as well. So the standard list inductor does take all of the arguments to the const cell, the term at the head term and the rest of the list, as well as, of course, the inductive value. So if you want to think about it this way, list.rec is actually a lot more like this fold prime you're talking about than the normal fold that we've written down.
Oh, okay, I see. Because I was wondering if this, like in general, you could always do this with like kind of like a fold, or if you needed to take like the rest of the stuff too, like if you had like a tree with multiple recursions.
Well, so they're not too different because you could take the rest of the list, this list A, and package it up into B.
Sure.
So like B here could be list A times B.
Yeah.
And the thing that you'd output would be B as well as that cons cell so that you keep track of it. And it'd be a little weird. The initial, you'd initialize it with nil, and it'd be a little weird because the output of that fold would also give you a copy of the list, which you didn't want to begin with. But it's you could throw that away and that would implement this fold prime. So there's no like deep difference between the two. Now, when we write down this recursor, each of these B's is going to be in terms of some specific list. So this is going to be, this list A is going to be called L, and this B is going to be some property of that list, and this is going to be, this isn't actually proper lean syntax, I'm just kind of ad-libbing here. So when we write down the recursor, the induction principle for lists, the elimination rule for lists, we end up needing to take this argument L just so that we can even state what B is about.
Sure.
So that's kind of why it's natural to, that's why the recursor is more close to this somewhat unusual fold as opposed to the standard fold. But they're not really that different. You can define one in terms of the other.
Okay, I see. So that's kind of like the dependent typing. Is it's like the type of B depends on this like type L or?
That's right. Yeah, and I guess next time we'll talk more about this. It's a little difficult in some sense to figure out how to organize a discussion of dependent types because I want to start with something that looks sort of more normal and that involves eliding over some details like how B can be about L to begin with.
Okay, that makes sense. I didn't know that I was missing something. I put a link in the chat about the paramorphisms. I think that I don't know if they're like generic over like lists or if they're like more type theory in general. But I think this.
Yeah, I mean you could. So broadly speaking, for any inductive type, you can write down that induction rule. So if you're thinking about a language like Haskell, where all data types more or less kind of are inductive types,
yeah.
Then for all of them, you can write down this induction principle. And that induction principle is always going to be of the form of what you're calling a paramorphism, except because in Haskell, you kind of sort of don't have type dependency. It's not going to be B of L, it's just going to be B. And
Yeah,
so it'll look a lot like
that.
that.
Was a weirdness for me. Okay. Thank you for helping clear that up for me.
Yeah, no problem. Happy to answer any other questions. Otherwise, see you on Tuesday.
No, thank you. See you on Tuesday.
Bye.